We are on 3C.12, equivalent representations of trig functions. Okay, this is a three-part section. The reason why it's three parts is because it's kind of a lot of information. We're going to be diving into our trig identities. You are going to have to memorize them. They're not going to be given to you. I don't want to tell you. Sorry. But they are our identities. Okay. So up first in part A. In part A, we're going to rewrite trigonometric expressions and equivalent forms with Pythagorean identity as our end game. Here are your identities. Okay. An identity is basically a statement that's been proven, so we don't have to keep finding or justifying it. This is just said to be true. Okay. So our most recent things that we talked about were our reciprocals of our trig functions. These are our reciprocal identities. Our reciprocal identity is just basically saying that sine x equals 1 over cosecant x, and vice versa. Cosecant x equals 1 over sine x. Cosine x equals 1 over secant x, and secant x equals 1 over cosine x. Tangent x equals 1 over cotangent x, and cotangent x equals 1 over tan x. Because they're equivalent, that means that they can be substituted in and out of different expressions and equations for one another. Okay? If you think about this in terms of our x's and y's, so in terms of x's and y's, if sine x is x, right? That means cosecant x is, sorry. Let me write. So this equals x. So this equals 1 over x. Does that make, not x? I'm writing x and no one's stopping me. How dare y'all? Why? Okay. That's how you feel. That just means you didn't know it, so you should be concerned. Because it's sine. Y. Okay? All right. Then next, we have cosine. Cosine is x. So therefore, when you write it in reciprocal forms, 1 over x is secant. That means from your unit circle, all you're doing is flipping the x coordinate. Does that make sense? So to find the secant, you just flip the x coordinate, and there's your secant, right? Tangent. Tangent is y divided by x. So therefore, cotangent is x divided by y. And are those not things that we can find on our unit circle? On the unit circle. Hence why it's in lockdown browser when you take this test. It's great. I know. Here we go. Quotient identities. Okay. Quotient identities are our division identities. Okay. So tangent and cotangent are two quotient identities. Tangent x equals sine x divided by cosine x. Okay. Because of this being true, this also means, anyone want to take a stab at it? Nope. This also means that it means secant x divided by cosecant x. Okay. And then therefore cotangent x is cosine x divided by sine x because cotangent is the reciprocal of tan. So this means that this also equals cosecant x divided by secant x. All of the identities are connected to one another. Next are my favorite Pythagorean identities. So way back when we were learning, the beginning of Unit 3, we talked about x squared plus y. That's not where I'm supposed to be writing that. Zoom type. X squared plus y squared equals r squared. Correct? Do y'all remember us learning that? Okay. So when we learned that, that's because we were working with this with our r being 1, right? Because it's a unit circle. And what do we say represented x and y on the unit circle? She meant to say cosine and sine. Yep, the cosine and the sine. So from this rule, created our Pythagorean identities. Our Pythagorean identity, the number one is sine squared x plus cosine squared x equals 1. Okay, that's essentially saying x squared plus y squared equals r squared, and our r equals 1. Does that make sense? From this identity, some really bored people sat around and said, if we plug in any of these, what else can we create? Okay, and that's what they did. They plugged in the reciprocal identities and the quotient identities to come up with two more Pythagorean identities. I just told you they were bored. I wasn't there. So these are your identities. So it came down to 1 plus 10 squared x equals secant squared x. 1 plus cotangent squared x equals cosecant squared x. All three of these identities can be manipulated to give you additional identities. Does that make sense? I can isolate sine x squared, right? I isolate sine x squared by subtracting cosine squared. So now I know sine squared equals 1 minus cosine squared. That's what it means to be manipulated. Okay, that's it. All right. One can also be secant squared minus tan squared. Make sense? Because all I did was subtract the tan squared. One can also be cosecant squared minus cotangent squared. All I did was subtract the cotangent squared. Again, meaning you can take these identities and you can solve for different parts, isolate different pieces of it. Okay. And then it gives you other identities. But as long as you know the baseline, then you're golden. Okay. Yes. No, maybe so.
Yes.
All right.
Let's say on the second part X, SEC or SCC?
SEC and the denominator. I'm asking you, are you talking about the denominator?
Denominator, yes.
SEC. All right, next are even odd identities. Even odd identities go as following. If you're asking for the sign of a negative angle, right, it equals the negative sign of its positive angle. That's all this is telling you. And the same for cosecant. If you're asking for the cosine of a negative angle, it's going to equal the cosine of the positive angle. Okay? If, say, for secant, if you're asking for the tangent of a negative angle, it's going to equal negative tan of x. And then cotangent. Let me tell you why. Let's go to our unit circle really quick that we drew out. That's not very pretty, but we drew it out, right? If I have a negative angle and I'm looking at it as the cosine of it, depending on where it's at, your cosine is going to be the same, right? So if I'm looking at quadrant 1 and quadrant 2, these cosine are both going to be what? Positive. And that's because your x's are positive in quadrant 1 and quadrant 4, right? I said 2, 1 and 4. If I'm in quadrant 2 and I'm in quadrant 3, notice that my x's are still both the same, right? They're both going to be negative. That's why cosine doesn't change just because it's a negative angle, okay? However, sine changes. So between these two quadrants, notice that in this quadrant, sine is positive, but in this quadrant, sine is negative. Okay. And when you have a negative angle, that means instead of rotating counterclockwise, you're rotating clockwise. So those angles are flipping or are reflecting across the x-axis. Does that help make sense on even odds? All it is a summarization of what happens when someone looked at the unit circle and said, oh, I want to know what is the sign of negative pi over 6. Well, negative pi over 6 is here. So the sign of negative pi over 6 is going to be the opposite of what the sign of positive pi over 6 is. Does that make sense? Huh? They were very bored people to recognize the patterns. But thanks to them, that's why y'all's little phones that you're addicted to, that's how they function so well because of trigonometry. So be thankful for very bored people. I don't know. Some of y'all are mildly addicted to your phones and gaming systems. So here we go. If you know the basic identity, it's easy to derive the others. So basically what this is proving how the other Pythagorean identities came into play. I can go through it and show you, or just show you that they can be manipulated. So you remember how we talked about with our unit circle, we had, here, we're just going to draw in a triangle. Going back to the old times when it was a little easier. Here's our Y, here's our X, here's our R. Remember those days? And then we evolved. We said Y is our sine and X is our cosine, and our radius equals 1 because it's a unit circle. Yeah. So then we came up, this is where this came from, where the Pythagorean, they're like, oh, so then sine squared of theta plus cosine squared of theta equals 1. That's where that came from. Does that make sense? How the Pythagorean identity first evolved? Makes sense? Are we okay? All right, perfect. Okay, so this is what you need to memorize. And I'm going to show you, if you, long as you memorize this, how to manipulate this to get the other identities. Okay, essentially all they did was two things. To get the second one with tangent, so this is the first Pythagorean, this is the second one, all they did was divide everything by cosine squared theta. Okay, so all they did was what?
Cosine.
Divide everything by cosine squared theta. So we're going to divide by cosine squared theta. So literally they went, you two are divided by cosine squared theta, and you're divided by cosine squared theta. By doing this, sine squared over cosine squared gave them tan squared theta. Cosine divided by cosine gives them 1, and 1 divided by cosine gives them secant squared theta. And that's how the second one came into play. Anyone want to take a stab at how they came up with the third one? If you said they divided by sine squared theta, you are so correct. So they came up with the third one by dividing by sine squared theta. So they took the original sine squared theta divided by sine squared theta plus cosine squared theta divided by sine squared theta equals 1 divided by sine squared theta.
Oh, I understand.
Sine divided by sine is 1. Cosine divided by sine is cotangent. And 1 over sine squared theta is cosecant squared theta.
I do have one question. It shows sin squared plus
It doesn't matter.
divided. So why don't you subtract cosine?
Mm.
First step?
No.
You're just gonna divide it?
Yep. I divide it. It's the whole thing. So sine squared divided by cosine. Do. Cosine divided by cosine. I just didn't want to write it twice. Okay. And does order matter when you're adding? No, it does not. So these are your three identities. Again, as long as you remember this guy, you can create the other ones. All they did was like, oh my gosh, if I divide by cosine squared, look what happens. And if I divide by sine squared, look what happens. Ta-da! Magic. Questions, comments, concerns? Okay, so purple, memorize. Then you can create the other two. Just simply dividing the purple by cosine squared or sine squared. If you want to remember all three, go for it. But you can create the other one from one. So less you have to memorize. Okay. No. This is actually my favorite part of trig. Like using the identities is my favorite part of trig. Like this whole section. Huh? This is my favorite part of trig.
I mean, this seems pretty easy.
Huh? I think of it as puzzles. These are my puzzle pieces, right? And I like puzzles. So these are my puzzle pieces. And how can I use these pieces to make things make sense?
I think it's pretty good. I just need to memorize the little equations.
Okay. All right, let's keep going. So it's saying we're using the quotient identity. So use the quotient identity to simplify and rewrite. When you are simplifying, rewriting, the goal is to get everything in terms of sine and cosine first. Okay? So your goal is to try to write everything in terms of sine or cosine first. Beta just means unknown angle, right? Okay, so we have cosine beta times tan beta equals sine beta. And it wants us to simplify this. All right. I don't think this is simplifying. We're just trying to get, this is our goal. Yeah. So we're simplifying, and they're telling you what you should simplify this down to, right? So sine beta is our end game. How can I take this and turn it into that? Well, first thing you want to do is think of your identities that'll allow you to change tangent into sine and or cosine. Which identity allows us to change tangent? Let's look at quotient. What does tangent equal? Sine over cosine. So I'm going to have cosine beta. But now, instead of tangent beta, we're going to write it in as times sine beta over cosine beta. And when I go through and I multiply, I have the same trig in the numerator as the same in the denominator. And what happens? They cancel. And did I come down to sine beta? Did I prove it? Yes, we did it. Okay. So again, now this is your end game. Give it a try. Your end game is tan x. Remember, you want to make sure that everything is in terms of sine and cosine before you dive in. Sorry for printing your papers wrong. I know it's annoying to have to keep rotating it. It, yeah,
I mean, you could just flip it.
true.
I think it's more convenient.
All right, which identity could you use to put this in terms of sine and cosine?
Why next one for
1 over cosine. So using reciprocal identity. So using our reciprocal identity, we can write this as sine x times, but secant x became
1 over cosine.
1 over cosine. I really need to change the pen tip of my writing pen. Okay. And then you multiply these two together, and what do they get? Sine x over cosine x.
Well, they do equal each other.
And what does sine x over cosine x equal?
Equal.
Tan x. Did I come down to the end game? I did. We are going to be taking notes all period because I don't see y'all again. Oh. Oh, we have 3 sections of notes left. That's it. I don't see y'all again this week. Nope.
Oh, we have one. See.
Why I said it's very crucial that we work all period. Yep. All right, here we go. Next, a big thing that you guys forget is that I modeled it in our example number 1 on purpose, is that when you're dividing over addition and subtraction, it can be separated into 2 separate fractions, okay? So when you're dividing a monomial, which is just one term, right? Monomial means one term. Under addition and subtraction, this can be split into 2 separate things. So when I split, this would become sine x over cosecant x minus cosecant x over cosecant x. Does that make sense? This is our end game, by the way. Okay. That's our end game. So sine x over cosecant x It's the same thing as sine divided by 1 over sine. And what do we do when we divide fractions? We multiply by the reciprocal. We keep, change, flip. So we're going to keep, change, and we're going to flip the reciprocal. Does that make sense? So we have sine x over 1 times, and what does cosecant x equal? It equals 1 over sine x. So when we flip it, it becomes sine x over 1. What is anything divided by itself? 1. So did we prove it? And done. Proved it. Cosecant divided by cosecant? All right. So notice here in this term, we have secant x squared and tan x. The goal here is to first write everything in terms of sine and cosine. How can I write secant squared x in terms of sine or cosine? One over cosine. So secant squared is going to become 1 over cosine squared. What does tan x become? Sine over cosine. You want everything in terms of sine and cosine. Remember, x's and y's run the show. Now that I have everything in terms of x's and y's, we're now going to just follow normal algebra. How do we divide fractions? Keep, change, flip. We multiply by the reciprocal. So we have 1 over cosine squared x times cosine x over sine x. What happens? What eliminates? So this one loses 1, this one becomes a 1. So we're just simply left with 1 over cosine. What is 1 over cosine? Oh my gosh, the tip of this pen is going to make me go crazy. And what's 1 over sine x? Did we prove it? We did. Yes. So when you divide anything out, cast with a friendly 1 is already there, always there. The only time it's 0 is if you're adding or subtracting, right? When you divide out, 1 is always there. Okay. So we divided out cosine x. It's still a 1 there. It's cast with a friendly 1. He's like, I'm here. I know you didn't see me, but I didn't go anywhere, guys. Okay. Did we see what I was telling you, that these are our puzzle pieces and all it's about is manipulating and eliminating? Okay. I would like for you guys to try 4A at your table. So you're going to try 4A. The end game is tan theta. So to take all of that and get it down to tan. That's your goal. You can do it. Remember, put everything first in terms of sine and cosine. Thank you. It's just puzzle pieces. The word problem. Like until section 13. Right now, we have to learn how to use them. See,
I have sine squared theta over one
Mhm.
here and then one over.
Mhm.
Even if this is in the middle, can I still? Okay.
Yep. You can eliminate across. That's what section 13 is. Don't worry. But if we don't know how to use the identities without being in the real world problem, honestly, your real world problems would more than likely be on the calculator part. So I wouldn't stress too much about it.
What does it mean by verify? Oh, I know.
This is what it means.
I understand.
Mhm. Are you ready to check? All right, let's look up. So sine squared is already in terms of sine, so we're gonna leave it B. Secant theta using reciprocal identity becomes 1 over cosine theta. Cosecant theta using reciprocal identity becomes 1 over sine theta. Okay, I have 2 sines in the numerator and 1 sine in the denominator, so I can cancel out one of my sines. When I cancel out one of my sines, I'm left with sine times 1 over cosine, which leaves me with sine over cosine. And thanks to the quotient identity, sine over cosine equals tan theta. All right. Next, we're going to do part B together. Like I want to go over meeting these lines. All right. So we have sine x, tan x plus cosine x. And the goal is to make this into secant x, right? All right. Sine is already in terms of sine. So we're going to leave sine alone. So we're going to let sine just be sine x over 1. How do I turn tangent into terms of sine and cosine? Sine x over cosine x. Plus, and cosine x is just cosine x. Okay? Before you can do anything, you have to make this into one fraction. So as one fraction, this becomes sine squared x over cosine x plus cosine x over 1. There we go. And what are we going to have to do? We're going to chopsticks and bold this bad boy. All right, so chopstick 1, sine squared x times 1 is sine squared x. My rights plus cross multiply, and we get cosine x times cosine x, which is cosine squared x, and then your bold. Cosine x times 1 is cosine x. What does this mean when you see that? Should think Pythagorean. What does sine squared plus cosine squared equal?
Equals 10.
Sine squared plus cosine squared equals 1. So this simply becomes 1 over cosine x. And what does 1 over cosine x equal?
Equals secant.
Secant. Did we prove it?
Yes.
We proved it.
I just didn't, I got to the last part, but I didn't know it had to go on from there.
Pythagorean.
Yeah.
So this is our first one that we've seen that we had to use Pythagorean identity to come into play. So the reason why your assignment has so many things is because there's so many ways that this can look, right? We can do as many problems over and over in different ways, but there are infinite possibilities of how this can look, right? So that's why it's not like, oh, let's go straight forward, let's do this, great. It's just that I'm trying to give you multiple ways that the problem can appear. Does that make sense? All right. Up next, verifying the identity using Pythagorean identities. So just like any other time that you're adding or subtracting fractions, they must have a what? Common denominator. And when they don't have a common denominator, what do? Right? You make it have a common denominator, okay? That's what the chopstick and the bowl method does. It helps you find a common denominator. Does that make sense? Okay, so we're going to practice that again on this one. So again, our goal here is secant x. Okay, right now, I cannot combine these two because their denominators are not the same. So I'm going to cross multiply.
Cool.
And we get cosine squared x minus sine x. And then that's going to be times 1 minus sine x. Order matters. Okay. All over. And what's my bowl? It's going to be 1 minus sine x times cosine x. And we're going to leave them what is that word that I can't think of? We're going to leave them factored. We're not going to distribute them. We're going to focus on the numerator. So focusing on the numerator, we are going to go through and distribute our numerator and simplify the numerator. Okay? So I'm distributing negative sine x, negative sine x. So we get cosine squared x minus sine x plus sine squared x. All over 1 minus sine x times cosine x. You cannot cross out over addition and subtraction. They're factors. You cross out factors, not terms. Okay? Terms are things that are being added together. So I cannot cross anything out because these two are being subtracted from that. Okay? Yeah. Because this isn't a factor. For if you have 2 plus 3 over 3, can you cancel out 3?
Yes.
No, you cannot. This is a term, not a factor. But if I had a 3 here, this is a factor.
Oh.
And I can cancel that out. Does that make sense? Okay. All right. However, I have cosine squared x plus sine squared x. Even though they're not next to each other, do I have that? Yes. Okay. Just because addition problems, the terms are next to each other doesn't mean they cannot be combined. So if I have cosine squared x and sine squared x, what does that equal? 1. So this now becomes 1 minus sine x over 1 minus sine x times cosine x. And now this is a whole factor. Because this is by itself, guess what I can do now? I can cancel it. When you cancel out a factor, Casper the friendly one is there. It doesn't become a zero. It doesn't go away. Casper the friendly one is like, hey, friend. And what does 1 over cosine x equal? Secant it.
That was pretty bad.
We did it.
Senioritis.
Huh? Nope. All right. Let's try this last one together. This last one is using an algebraic technique. Does anyone remember what a conjugate is? A conjugate. Yes.
Cosine squared x minus sin x plus sine squared x. Wouldn't the sin x and sin squared x, the negative sin squared x, combined to make them sin x?
No, they're not the same. It's just like if you had y squared minus x plus x squared. You couldn't combine these two. They're not like terms, right? So that's what that is. But we do know that y squared plus x squared equals r squared, which is what? 1. Okay. All right. I don't know why this box like that. Just roll with it because I'm getting tired of erasing. And I promise by next class I will have a new tip for my pen. Guess it's that the year is almost up and it's almost up. So
Oh,
all right. So what we're gonna have to use here is called a conjugate. Okay. The reason why we're using a conjugate is because there's nothing else for us to manipulate. And all this obviously did was flip-flop itself around. So we're gonna reintroduce the word conjugate. Okay. Conjugate means you have the same terms, opposite operation. Okay. Meaning that if I'm adding, then my conjugate is subtracting. If I'm subtracting, means my conjugate is adding. Okay. So we're going to be using this. So we have cosine theta of 1 plus sine theta. And we're going to multiply it by its conjugate. So its conjugate is just simply 1 minus sine theta. Because your terms stay the same, but your operations are going to change. Okay. This is just a fancy 1. Anything divided by itself is what? 1. So am I really changing this problem that much? No. This is difference of 2 squares. Because what you do to the bottom, you have to do to the top so that it stays balanced. This is just a fancy 1. Okay. What you create on the bottom is, do y'all remember the term difference of 2 squares from Algebra 2? I had to take my posters down, so I can't point to it. But difference of 2 squares just means that if you are subtracting 2 perfect squares, then their factors are just going to be the square root of the first term plus or minus the square root of the second term. You all remember doing that vaguely? This is what we did. This came down to being a difference of 2 squares situation. Okay. So when we multiply this, this is going to become cosine theta times 1 minus sine theta over, and this difference of 2 squares becomes 1 minus sine squared theta. Okay, remember I told you all that the Pythagorean identities can be manipulated, right? So we know that our Pythagorean identity, we have sine squared plus cosine squared equals 1, right? If I subtract sine squared, what am I left with? I'm left with 1 minus sine squared. So therefore, when I see 1 minus sine squared, I can substitute it in with cosine squared. So this can be substituted in with cosine squared. So going back to my problem, I'm left with cosine theta times 1 minus sine theta. Now, substituting in cosine squared theta.
And we can't replace the other one because that's not a fact. This rule is squared, right? We can't do one time calculation.
Exactly. I have a square in the numerator, and this is a factor because it's being multiplied, right? Factors are numbers that are being multiplied. So we came down to it. 1 minus sine theta all over cosine theta. And we proved that they are equal. Okay, so again, summarize what we had to do with this one. We had to use the conjugate rule. The conjugate technique, not rule, technique, is just same terms, opposite operation. The reason why you use this most times is to, one, if you're working with radicals, but also to be able to create difference of two squares situation. Okay, that allows me to now say, okay, I have factors that are opposite operations, therefore they're difference of two squares, and I get 1 minus sine squared. If you do not remember what I mean by difference of two squares, let me show you really quick. If you have x squared minus 4, this is a difference of two squares, correct? And we learned that to factor this, it becomes x minus 2 times x plus 2. Does that make sense? So this is the difference of two squares. If I was to re-multiply, distribute all this, it comes back to x squared minus 4 because your middle two terms are going to do what? Cancel out because one is positive and one is negative. Okay, so that was the goal here, was to create a difference of two squared. You may remember me saying dots or not if you have me for algebra 2.
I remember the term.
Yes. Okay. All right. So that concludes part A, right? Dun 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 dun.